Okay, so I have a big pleasure to introduce Bogdan-Matioc, and he will speak about a very interesting problem on this two-phase Stokes flow by capillarity in the plane. And yeah, so please.
Okay. Hello, everyone. Thank you, Sharka, for the kind introduction. I would also like to thank the organizers for the kind invitations and also for the possibility to talk. I will talk today on two recent joint works with my co-author, Georg Prokert from TU Eindhoven on the two-phase Stokes flow by capillarity in the plane. So let me start. The outline of my talk is as follows. So I will first present the mathematical model, which is a quasi-stationary Stokes flow, and then in 2D. And then in the second part, I will present the main result and also some ideas of proof. So let's start with the mathematical model. So we consider the quasi-stationary Stokes flow in the plane. So we have two fluid phases. These are which occupies the domains omega minus of t and omega plus of t. And these two phases cover the entire plane. So the fluids are unbounded in this direction and also above. These two phases are separated by a sharp interface, which is an unknown of the problem and which we parameterize as a function or depending on the time t and the horizontal variable x1. And we are, as I already mentioned, in 2D. So we have to say what happens at infinity. So we assume that we have asymptotic boundary conditions. The flow is almost stationary, far away from the origin, meaning that the velocity is almost zero, and also the pressure is almost zero, and the function f as a function of x1 is almost zero, is flat. So we will denote by mu the viscosity of the fluids, and we take into account surface tension effects at the interface between the fluids. So we will denote for with sigma, which is a positive constant, the surface tension coefficient at this moving boundary gamma of t, and gravity effects are excluded. So we neglect gravity. So the equations of motion are the incompressible Stokes equations. So we consider the quasi-stationary problem where we do not have a time derivative here for the velocity. Yes. So we have the quasi-stationary Stokes equations. The fluids are incompressible, and the divergence of the velocity is therefore set to zero. And this is in both domains. And v plus or minus is the velocity of the fluid in omega plus or omega minus, and we write p for the pressure. We have also boundary condition, which are the usual one. Before explaining the boundary condition, let me first introduce some notation. So if we have a function z which is defined on R2 without gamma, then we denote by z minus and z plus the restriction of this function to the domain below the graph and above the graph. And the jump of z at the point x, which is on gamma, is denoted with square brackets as usual. And this is the limit when we approach this point from above minus the limit when we approach the point from below, if both limits exist, of course. And we do also vice versa. If we have a function defined in omega minus and one defined in omega plus, then we define the function z as being the characteristic function of omega minus multiplied by z minus plus the characteristic function of omega plus times z plus. And in this way, we have constructed a function which is defined on a whole R2. Without gamma, but it's defined almost everywhere. So the first boundary condition says that the velocity is continuous on gamma of t, the jump of the velocity is zero. And here we have a condition on the jump of the stress tensor. So the jump of the stress tensor multiplied by mu. Mu is a unit outward normal at the boundary of omega minus pointing in into omega plus, so this is new. And on the right, we have minus the surface tension coefficient. Kappa is the curvature of gamma of t, and u is again the unit normal. And the stress tensor is defined as usual, minus pressure times the identity plus the mu times the symmetric part of the gradient. Okay, these are the boundary conditions on gamma of t, but of course we have far-field boundary conditions. So when the horizontal variable, which we denote sometimes by c, goes to infinity, f has to vanish, and also the velocity field and the pressure vanishes far away for large x. And finally, we have a condition which says that the normal velocity of the interface gamma of t equals the normal component of the velocity fields of the fluids on gamma. So it does not matter if you have plus or minus, because if you remember, the velocity is continuous across gamma. So altogether, we arrive at the following system, which is a quasi-stationary Stokes problem, and where I summarized here the previous equations, and we are given an initial condition for the interface f. F at time 0 is equal to f0. And this is a moving boundary problem because the equations are defined in domains which are unknown and evolve in time. So we have three unknowns, the function f, which parameterizes the interface, the velocity field, and the pressure. As a result of this problem is nonlinear. A nonlinear evolution problem, but it has a quasi-linear structure because we have this curvature term here, and the curvature is the second derivative. So second derivative means derivative with respect to x of f plus 1 divided by 1 plus f prime squared to the power 3/2. And if the phase space is a space where the functions are quite regular, then at this point we require the highest regularity from f to define the second derivative. And the curvature is linear with respect to the second derivative of f. So, and this is something which can be then transferred to the evolution problem. And our strategy to solve to prove well-posedness of the problem is to solve the free boundary problem described by the first 6 equations. So we assume that f is given, so we know omega of t and gamma of t, and then we can solve b and p explicitly in terms of f. And here we take advantage of the fact that the equation are posed in the entire R2. And an important observation here is that these equations, the first 4 equations are all linear with respect to v and p and have constant coefficients. And because of this fact, one can use potential theory and one can derive for v and p explicit formula, so expressed as contour integrals over gamma. And in this way, we can express the traces of b on gamma explicitly in terms of f via certain singular integral operators. And at the end, from the last equation, we obtain an evolution problem for f. So f is the only unknown at the end, and on the right, we will have certain singular operators which have kernels that depend on f, are expressed in terms of f. On the Stokes problems, there's a lot of literature, but the quasi-stationary problem is, I guess, less studied. So I have here just 4 references. And all these references consider the setting where omega of t is a bounded domain. And in the first references, a reference of Günther and Procher from 1997, they consider the problem in arbitrary space dimension, and they prove well-posedness for h k initial data where k is larger than 3 plus n plus 1/2, n is here as a space dimension. Then 2 years later, Solonikov has also proved local well-posedness for initial data in C3 plus alpha, where alpha is between 0 and 1 in 3 dimensions again. And 2002, there are 2 papers of Friedman and Reitig where they consider the problem in 2D and in 3D. In the second paper, where in 2D, the initial data are from H5, and in 3D, they are from H6. And more recently, Jan Pruss and Thierry Simonet, in their monographies, they have also studied the quasi-stationary Stokes problem, and they have established well-posedness of the problem in the Sobolev space. In the Sobolev space, where p is between 1 and infinity, is arbitrary, and here we have a constant mu, and the assumption on mu is that it's less equal to 1 and is larger than n plus 2 over p. So from this inequality, one obtains that actually p should be larger than n plus 2, where n is a space dimension. So p equal 2 is excluded even in 2 dimensions. So all these references consider a bounded domain, but they also establish well-posedness in different spaces, but all these spaces are embedded in C2. Now, an important observation is that if we have a solution to the Stokes flow, we can define another solution. For each positive lambda, the function f lambda, which is defined as by this formula, is again a solution. And by a scaling invariance argument, this identifies in 2D the Sobolev space H3 as a critical space for the Stokes problem. And our goal was to extend the well-posedness result to all subcritical spaces HS, where S is between 3/2 and 2. So up to the critical regularity. Some observations. If F is in HS with S between 3/2 and 2, the curvature operator is no longer a function, yes, because here we have second derivative of F. Of course, we can view this as a derivative, namely the derivative of F prime over omega, where omega is a square root of 1 plus F prime squared. And in this way, we can view this as the derivative of a function from HS minus 1. But this is a distribution. With respect to our analysis, an important observation is the following. So in this boundary condition concerning the jump of the stress, we have on the right the term k nu, kappa nu. If we multiply it by omega, then this term is a derivative. Namely, the derivative of a function g, which has 2 components, g1 and g2. And g1 is given by this expression with, again, the same omega, and g2 is defined by this expression. So you see that in both cases, g1 and so both components g1 and g2 are nonlinear with respect to f prime, because we have f prime in the denominator here in the root, but also in the numerator. So G is a fully nonlinear operator with respect to f, and this is a function which appears in the formulation. We will not see any longer the curvature, but this 2 function will appear in the formulation, and because these 2 functions are nonlinear with respect to f, our formulation will be a fully nonlinear evolution problem. And now let me come to the main result, where we establish the well-posedness in this subcritical Sobolev spaces HS with S between 3/2 and 2. So we have 2 papers. In the first paper from 2020, we have considered the case where the viscosities are equal. And in the paper from this year, we have considered the general case where the viscosities may be different. And the well-posedness result is as follows. We are given a function f0 in a HS an initial condition, and then we obtain a unique maximal solution FBP to the Stokes problem, and the function f is continuous up to time t equals 0 in HS. So in this sense, because of this property, the initial condition can be satisfied in classical sense. And the function is C1 into HS minus 1. So this is a first order problem. The velocities are C2 in the domain and C1 up to the boundary, and the pressure are C1 in the domains and continuous up to the boundary for positive times. And also for each positive time, the trace of the velocity on the interface is H2. And T plus is, as always, maximal existence time, and this is well-Posner's result because we have also a sentence saying that the solution depends continuously on the initial data. Additionally, because the problem is parabolic, we have also some parabolic smoothing. So for positive times, the interface is smoothed as a function of time, but also of the horizontal variable psi. And moreover, the function is C infinity for positive time in hk for each k. So for example, we can choose k equal 2 or 3. And because of this property, all the equations in the classical formulation are satisfied pointwise in classical sense. And we have also a result saying that the solution exists globally if for each time t positive, we can bound the supremum of the HS norm of the solution on the interval 0 t intersected with the maximal existence interval. So this can be rephrased by saying that if a solution is not global, then the HS norm explodes when approaching the maximal existence time. And then now I will present some ideas of proof. So if one has a bounded fluid domain omega t, then the usual method to solve such moving boundary problem is to transform the problem on a fixed reference domain omega. And one chooses a domain omega with the boundary psi, mu, n is the outward unit normal. And this can be done by using the Hanzaba transform, and this is something which I have used in my research, but also Lagrangian coordinates. So the idea is that the interface gamma of t should be represented as the graph of a function rho over psi, over sigma. So for each one chooses a function rho, which satisfies some bounds on its norms. C1 norm, for example, should be sufficiently small, and then if one starts with a point on psi, the function rho tells you is a sign distance from this point to the boundary of omega of t. This boundary is then the graph of rho over sigma, and it's then and depends on rho of t, and also the fluid domain is then parameterized by rho. And using this rho, one can construct the so-called Hanzaba transform psi rho, which is a diffeomorphism from omega to omega of t. And then one uses this diffeomorphism to pull back the equation on omega. This is very useful because in this way, one obtains a problem which is posed on a fixed domain. One can introduce solution operators, study their dependence on rho, and so on. So the new unknowns are in this for the pullback problems is the function rho, and the pullback variables, the pullback pressure, velocity, and the pullback pressure. This approach has, however, some drawbacks. So, for example, here in the fluid domain, one has Stokes equations, and when pulling back these operators on omega, one transforms the Laplace operator into an elliptic operator, which is uniformly elliptic actually, but has coefficients which depend nonlinearly on rho. And then also the gradient happens something similar. And then one obtains here in the fluid domain boundary value problem for rho, for the velocity and the pressure, which is then solved independence of rho. So one identifies the velocity and the transform pressure in as a function of rho by introducing certain solution operators to Stokes boundary value problem, but the dependence of rho is very complicated because these operators depend on rho nonlinearly. At the end, the problem is then formulated as an evolution problem only for rho, where on the right-hand side we have a nonlinearity, capital calligraphic F, which involves solution operators to rho-dependent equations. In the unbounded setting considered in this talk, where the fluid phases cover the entire R2, the solution operator are more difficult to introduce because solving elliptic equation in unbounded domains is more difficult. And also when introducing this Hanzava diffeomorphism, one needs certain smallness assumption on rho. And these aspects can be overcome in our setting by using potential theory to determine V and P explicitly in terms of F via certain integral representations. And this is something which appeared first in a paper of Badia and Duchamp from '98. But this is also something which is widely used in the context of the Musket problem. So the Musket problem is a similar problem, but the similar moving boundary problem. One difference is that Stokes equations are replaced by Darcy's law. So Darcy's law is this linear relation between velocity and the gradient of pressure. Here mu is the viscosity and c is a constant. And this approach has been used recently very often in the context of the Musket problem. So in the end, one obtains an evolution problem for the interface F. But now the right-hand side is explicitly defined in terms of singular integrals operators. So there are no smallness assumption required on F any longer. And this operator, at least in the case when the viscosities are equal, can be written down. It's an integral operator. And this is very useful because then this equation can be defined for functions f which have low regularity with respect to the x variable, with respect to the horizontal, to the space variable. So let me point out how to obtain this formulation by using potential theory. And so the first goal is to solve the Stokes boundary value problem. These are the first 6 equations of the system. And this is done by fixing a function f in H3. This is given, and then the result says that the Stokes boundary value problem, which we call the fixed time problem, because we fix time, has a unique solution. V and P are uniquely determined by F. And if the viscosities are different, we have to assume additionally that the velocities on gamma are H2. So the uniqueness holds when the viscosities are different under the assumption that in the class of solution which restricted to gamma are in H2. So the proof is technical, especially when the viscosities are different. But the message is that V is determined explicitly in terms of contour integrals. And now I will point out how to determine V in the case when the viscosities are equal, not equal, because this is a simpler case. So some formal computations leading to a formula for V in the case when the viscosities are equal, then we denote them by mu. And here we do what I mentioned before. So we have V plus above, V minus below, and we view the velocity now as being defined on whole R2 without gamma. And similarly for the pressure. So the pressure is defined by P plus above and P minus below the interface. And then we can compute the Stokes, compute this differential operator in the sense of distribution on R2, on whole R2. And one uses Stokes formula and some integration by parts, maybe, and then one obtains that on the right, this is a distribution which is supported on gamma. So this is a Dirac distribution on gamma. And here we see that the right-hand side in this boundary condition for the jump of the stress tensor. So we have identified this distribution. It has two components, F1 and F2, which is given by this formula. And fortunately for the Stokes equation in R2, there are fundamental solutions. There are two of them, U1, UK, PK. UK is the velocity, and PK is the corresponding pressure, and K is 1 or 2. And they are given by this formula. And important is this term, this logarithm term, which is a problem. But if we use at a certain point integration by parts, we can get rid of the logarithm and obtain a similar term as here. And this is this observation where we use this observation that nu k nu is the derivative of this function g prime. So this function can, because we have a derivative, we can integrate by parts at a certain point and get rid of this logarithm. So we know what this distribution is. We know the fundamental solution to the Stokes equation in R2, and then we can identify the velocity and the pressure simply by convoluting the fundamental solution with the distribution. And here we use the standard summation convention. This is U1 convoluted with F1 plus U2 convoluted with F2, and similarly for the pressures. And now, this is a formula. So V of x is the integral over R squared, UK, x minus y, Fk. So this is the convolution of UK with Fk. And this is all this is formal. So Fk is something supported on gamma, as I mentioned. So the integral is actually only on gamma, and then we replace Fk by this. So we replace Fk by what it is. So we have sigma, which comes out. We have the curvature, and we have the kth coordinate of nu. So nu, the outward normal, has two coordinates, nu1 and nu2. Okay, and now we write the integral not over gamma, but over r. And because we do this, we obtain this term omega pops up. So omega, remember, is the square root of 1 plus f prime squared. And now we use the observation that omega k nu is the derivative of g, and integrate by parts. And in this way, we move the derivative from g to the fundamental solution, and we get rid of the logarithmic term. And this is something which makes sense for f in H3. So for each function f in H3, this function v of x is well defined on R for x in R2 without gamma. And a similar we have a similar formula for the pressure. And now the idea of proof is the following. We start with these formulas and we prove that they are the solutions. And then we also prove uniqueness. And there is this, in the system we have an equation left, namely the equation for the normal velocity of the interface, which will give us the evolution equation for f. So we need to compute the traces. So this is an equation of gamma. We need to compute the traces on B on gamma. And this is done by using Plemel type formulas. These traces can be computed, and they are expressed in terms of certain singular integrals, which we call BNMO, and were introduced in these two papers in the context of the Musket problem. So I will come back to these operators later on. But from this formula, we can determine the trace of the velocity on gamma, and this is expressed in terms of this operator, and we obtain the formulation. So we use this boundary, so the evolution equation for the interface, and we arrive at this evolution problem where cal f of f is defined as minus f prime v1 plus v2. Yeah, this is the right hand side. And v1 and v2, as I mentioned, the traces on gamma are defined by using these operators b and mo. And these operators are singular operators, depend on f, and they are evaluated at this function g, with g prime equal omega k nu. So here we have everything is explicit in terms of f, and because g depends nonlinearly on f, we have a nonlinear operator here. This formula for the velocity is well defined for f in H3. However, this right hand side is well defined also for f in Hs with s larger than 3/2. Because in the definition of this singular integral operators, it is needed that the function is Lipschitz continuous. So here we need that f is in W1 infinity, and this is satisfied for s larger than 3/2 in one dimension. And here the definition of g appears f prime, so everything is well defined. So this problem is then an evolution problem for f in Hs. And let me now point out what happens in the general case when the viscosities are not equal. So mu plus minus mu minus can be any real number. We obtain a similar, I do not go too much in details here, but I will only point out the abstract formulation. So we obtain a similar evolution problem for f. But remember, before we have here v1 and the traces of the velocities. Now we have two functions, beta1 and beta2, which are no longer locally explicitly expressed in terms of f. So beta, this is the density of a singular integral operator. It has two components, and it is determined by solving this equation. So on the right, we have the identity plus twice a mu. A mu is this coefficient, real number, and it is important to point out that this number is between -1 and 1. And d of f is a singular integral operator, namely the double layer potential for the Stokes equation. And it is again an operator which can be, is a singular integral operator which can be expressed in terms of this BNMO singular integral operators. And on the right, we have again twice a mu, and here we have v1 restricted to gamma, v2 restricted to gamma. These are not the velocities for this general problem. These are simply these expressions. So the right-hand side is explicitly with respect to f, but we have here to invert this operator. And this can be done because twice a mu absolute value is less than 1. Less equal to 1. And this is a real number. And then one can show that if the coefficient here is less than 1, then one can invert this linear operator, and this way one determines beta explicitly in terms of f, but we have additional non-locality because we have to invert the operator. So the inverse pops up on the right. An important observation is that if a mu is 0, then this term vanishes, and we obtain for beta this expression. And we have here in a mu this numerator, but this formally simplifies with this one. And then the right-hand side is exactly this one. So in the case when the viscosities are equal, we recover the previous formulation from the case when the viscosities are different. So in the case when the viscosities are different, we need to solve this equation, and the solution operator, so we determine then beta independence of F induces additional non-linearities and non-localities. And the invertibility of this operator was done by using some underlying Rayleigh formula for the Stokes equations, and we were inspired by a paper of Chang and Pak from 2009, where they consider this invertibility issue in the setting of a bounded domain. However, we have here an unbounded domain, so we had to use also some different arguments, and we also use some Rayleigh formulas for coming out from the Musket problem when inverting the operator. But after inverting the operator, we obtain this this evolution problem for F, and then we have to establish two important properties in order to prove well-posedness. So the first property is that the operator F depends non-linearly on the unknown, depends smoothly on the unknown as an operator from HS to HS minus 1. And then we show that the problem is parabolic in the sense that the pressure derivative of F at each F0 in HS generates an analytic semigroup in this space of bounded operators. And this properties identifies the Stokes flow as an evolution problem. And for this type of problems, we can use abstract results. For example, we are grateful to Alexandra Lunardi and her manuscript monography, where she presented a theory which applies to such problems. And then we obtained the well-posedness result I have presented you. So these properties, the smoothness and the generator property for the pressure derivative, are essential for our analysis, and they rely on the properties of these operators B and MO, which I will now introduce. So we are given two natural numbers N and M, and Lipschitz continuous function. A is a nonlinear variable because it appears to the square and in the denominator, and we have n linear variables d1, dn. These are Lipschitz functions, and we have another linear variable which is called h, and this is should be seen as an L2 function. And this operator evaluated at psi is defined as 1 over pi, the principal value integral. So let's forget for a moment this term. So what we have here is psi of h of psi minus s over s. 1 over s is not integrable close to 0, so this is the principal value is needed. And what we have here is simply the Hilbert transform. Okay, so this is these operators B and M are generalization of this of the Hilbert transform, because here we have a kernel where this function B1, Bn, these linear variables, and the nonlinear variable A pops up. And we have in this expression always terms of the form delta Bi over S. And this delta psi as Bi, so of U is simply U of psi minus U of psi minus S over, and we divide it by S, and because the function ellipsis continuous, this is a bounded term. Yes. Okay. So if n is 0 and n is 0, then the product is 1. If a is 0, then we have no denominator, and Bnm 0 is a Hilbert transform. And as I mentioned, a is a nonlinear variable, the b1, bn are linear arguments. However, in the context of the Stokes flow, it always appears that a and b1, bn, they are always f. And because of this, we denote by Bnm O of f simply Bnm when a is f and b1, bn are f. So this is a function of this L2 variable h. And this is R's operator in singular integral operators in the abstract formulation, and this operator have to be well understood. We have established several results on this operator, partially alone, partially with Helmut Abers, my colleague from Regensburg, and with Georg. So if A, B1, Bn are Lipschitz continuous, then as a mapping depending on H, this operator is bounded from L2 to L2, and its norm is bounded by a constant which depends on Nm and the Lipschitz norm of A. And here we have the product of the Lipschitz norms of B1, Bn. And the proof uses a deep result from a harmonic analysis, which is due to Takafumi Murai. Once this result is available, so when we were at the point that to realize that we have this result, then the boundedness is quite easy to be shown. Now, if the function A, B1, Bn are more regular, so they are from Hs, where S is between 3, half, and 2, so A is also from Hs, then as a function of H, this operator are bounded on Hs minus 1, and we have a similar estimate for the norm. We have this constant, which depends on these quantities, and here we have the product of the Hs norms of the operators I. And lastly, these operators, BNMO, defined in this way, they depend smoothly on F as mappings from Hs to the bounded operators on Hs minus 1 of F. So if A, B1, Bn are all in F equal to F and F is in Hs, then this operator is bounded from on Hs minus 1 of R, and the dependence on F is smooth. As the smoothness property of the non-locality CalF of F is a consequence of this property, and it remains to discuss the generator property for the Fisher derivative of F. So the first step is, of course, to compute it, and this the derivative, which is a linear operator, can be expressed again in terms of this operator's BNMO. Well, this is almost true because we have the following formula. So in the Stokes problem, m is always 2, therefore here we have a 2. If we differentiate the operator with respect to f at f0, on the right-hand side, we do not have the operators BNMO because you see here the first variable is the linear variable f. But there is this, we have a kind of commutator property. So what we can do is f can takes the place of h, and it appears with a prime, and we can pull h out of the operator, put it in front. And in this way, we obtain this operator, h times bn minus 1 mo, evaluated at f prime. Yes, and this is a leading order operator because it's hs minus 1 norm of this difference is bounded by a constant, the hs minus 1 norm of h, but the norm of f is not taken in hs, but in hs prime, where s prime is any constant between 3/2 and s. So the difference is of lower order with respect to f. So at the end, the Fisher derivative can be expressed in terms of these operators again. So if f0 is 0, then the Fisher derivative is a nice operator. It's a Fourier multiplier. Namely, we have here this negative constant, and here is the square root of minus Laplacian. And this is a Fourier multiplier, generates an analytic semigroup by standard Fourier analysis methods. If f0 is, however, different from 0, the Fisher derivative is no longer a Fourier multiplier because we have the singular integrals operators appearing in the formula. What can be done is to locally approximate this operator by Fourier multipliers of the form alpha times the Fisher derivative of f at 0 plus beta d over d psi. So this is the differential operator d over d psi. This is a first order operator. Yes, it's clear. This is a first order operator, and these constants alpha and beta are in fact uniform. So they are, alpha is strictly larger than eta and is is larger or equal eta and less equal 1 over eta, where eta is some constant between 0 and 1, and also beta in absolute value is less equal to 1 over eta. So these Fourier multipliers are, these are the Fourier multipliers which approximate locally this pressure derivative. I will come in a moment to this. And the observation is that these coefficients are uniform, belong to certain uniform interval. And this is a generalization of the method of freezing the coefficients of elliptic differential operators, just that now we have not elliptic operators, we have singular integral operators. And then one can use these operators are all generators of analytic semigroups, and they satisfy, and their resolvents satisfy certain uniform estimates because of these two properties. And then one can use a strategy which I have learned from these papers. Joachim Escher was my PhD advisor. And one can then transfer the generator property from these Fourier multipliers to the pressure derivative. And the whole analysis is again built up. We have to localize this operator, so we have to look to know how to localize these operators BNMO. And here I present a result obtained together with Helmut Abels, but there are similar results with Georg Proker, established with Georg Proker. So for the localization, we use a so-called epsilon localization family, which is finite. Epsilon is between 0 and 1. And this family has a finite number of functions. So, so first of all, the functions pj epsilon square, they are a partition of unity. So the sum is 1. And there is a special function in this family. This is the function with j equal capital N, which is a function which is 0 between -1. This is a function in red. This is 0 between -1 over epsilon and 1 over epsilon, and it's 1 immediately afterwards. And this, the other function of the partition are pointed out by green. These are functions which have a small support of size epsilon. And yeah, they are also equal to 1 here. And psi j epsilon, this is a point belonging to the support of pi j epsilon. And the localization result is as follows. We are given, we choose again S prime between 3/2 and S, and we give ourselves a small constant nu, which is arbitrary constant. And then we can find for sufficiently small epsilon, so if epsilon is very small, we have that this operator can be localized in the following sense. This, we multiply it with the function pi j epsilon, and this operator can be approximated by a Fourier multiplier. Here we have the Hilbert transform evaluated at pi j h, and here we have constants. This is a constant. And what we do when localizing is, remember, we have all these quotients delta psi s f over f. This is replaced by the derivative. Okay, let's write f0. This is replaced by the derivative of f0 at psi j epsilon. So we have in this way this coefficient here, which is a real number. And the approximation work, so this operator can be localized by this Fourier multiplier, because on the right-hand side we have this arbitrary small constant nu times the full norm of pi j h. And then we have a constant capital H, and here we have a lower norm of small h. Yes. And this is true for j between absolute value of j less equal n minus 1. There are also other results for j equal n and so on. But once we have these results, then we can localize the pressure derivative in the way as I mentioned before. If we multiply it with a function of the partition, we can approximate it by this Fourier multiplier. The Fourier multiplier evaluated at pi jf, and here we have the full norm of pi jf, and here we have a lower norm of f. The constant k is large, depends on epsilon, but this does not matter. This is how the localization procedure works, and once we have this, then from the generator properties of this Fourier multiplier, we can deduce a generator property for the pressure derivative of KLF. And the well-posedness and the criterion for global existence followed then by using the abstract parabolic theory of Alessandra Lunardi with a slight improvement concerning the uniqueness of the solution, but I will not go into detail here. And the parabolic smoothing property uses a translation invariance of the problem with respect to horizontal variables via the usual parameter trick. And here on the last slides, I have the references. So the first paper has been published in the Proceedings of the Royal Society of Edinburgh, and the second one can be found on arXiv. And with this, I would like to thank you for your attention. Thank you very much.
So thank you very much for your very nice and very interesting talk. So I would like to open discussion. So there are some questions or remarks. Yes, please, Professor Saito.
Thank you for nice talk. I have a question about can you say something about the decay time decay estimate for the solution F?
So how f decays at infinity?
Yes.
No, we did not consider this point.
Okay.
So we have this result that f is in all hk, but this does not give you so much. Yes, the solution for f of t with t positive is in all hk. For all k.
Okay. Okay.
But we do not have more.
Okay, thank you.
Thank you.
Okay, so are there any other questions or remarks? It seems to be not the case.
Keiichi has a question.
Yes, please. Sorry, I don't see.
So I think you do not mention about the densities of the fluid.
So we neglect gravity here.
So is it important that you assume that the densities of two fluids are equal?
So we do not assume this. We do not have, you do not see the density in the model. We neglect gravity.
Sorry. Okay, I understand. Thank you.
And we cannot, so to be honest, we cannot incorporate gravity because the gravity, we cannot use this trick. So when we have this formula, we have here the curvature, and this term is a derivative of a function gk, and this function g is from h2, and then we can integrate by parts, and we get rid of this logarithm. If we have gravity, we cannot do this trick, and then this formula, formal formula which we obtain is no longer is meaningless.
So if you have the gravity, then the story might be quite different from this one.
Yeah, so this approach is it's not clear at the point how to tackle this when gravity is incorporated. Though gravity has lower order, yes?
Mm-hmm. I understand.
Gravity has lower order compared to surface tension.
Thank you.
You're welcome.
Okay, very good. So I'm just watching if there are some more questions or remarks. Yeah, maybe I was thinking during your talk, what will happen, because you assume that you have continuity of these velocities on the boundary. Yes. So natural question is if you have just continuity in the normal direction.
Continuity in the normal direction.
Just in normal direction.
So then you have less here, less information.
Of course, then you need to add something probably still. Because let's say fluid structure interaction, we know that if you have just continuity, let's say between bodies and fluid, just in normal direction, then you need something more. Of course, then you need some, let's say, Navier type of boundary condition, because you have this slippery. So somehow, probably then you will need also something like this.
Yeah, so maybe change both then. Boundary condition on gamma. Yeah, maybe. I would expect that this works because what we use here is to solve this problem is this integral potential theory approach, and I would guess that one can modify here the boundary conditions. But then one has to see what one has.
May I ask you? I mean, maybe the point already Sharka, the point.
Yes.
Then don't you have any kinetic condition? Yeah, because gamma is originally moved, right?
Gamma moves, yes.
Therefore, you have the evolution speed of the gamma.
Yeah,
but then it's a v. Your v statics velocity v doesn't depend on t, or does depends on t. I don't catch you this point.
This one.
So we have this quasi-stationary Stokes flow. We have the interface moves with this.
Yes, this one, yeah.
So what we do is at each fixed time, we solve this. V is a function of f of t, of course. But this is we call fixed time problem because at each fixed time we solve this first 6 equations. Yeah, so
for each t, so yes, I see, understood. So for each t you have statistical equations. Okay.
So this is v of t and x actually, yes, and here f is of t and x, and gk is of t and s.
So you consider the stationary solutions in some sense.
No, this is quasi-stationary problem.
Then my question again the same, because the evolution speed of the gamma t is defined by this last equation.
Yes, and
then the v. So the v plus minus is also depends on the function of f of t.
Yes,
if
you're right.
So f is, for example, the description of your gamma t.
Yes.
Okay. Definition function. Yes, I see.
So we have at this point this formula. V depends on time and x. So here I write just f. F is actually f of t. Yeah, and we determine v of t and x, and then we compute the traces. These are all here we have not f but f of t, of course, and g is g of t. And here is the evolution equation for the interface. From this,
okay, I understood now. Okay, so you get this evolution equation from this kinetic equation.
Yes.
Okay.
Exactly.
Okay.
So the fixed time problem is a problem without the full system without the evolution equation, and from the evolution equation we obtain then the evolution problem for f. Yeah.
But I'm also afraid that you have overdetermined or not. I don't know. But
no.
Because how many equations? You have 2 equations, essentially.
This is a system. Has a unique solution.
But unknown is only f, right?
So f is given and the unknowns
are v and t, right? No? F is a scalar function.
V is a velocity.
Yes, it's understood.
And p is
so velocity is also the unknown, but
yes.
Yes.
This is not overdetermined. The solution is unique. So we have this formula.
Okay, so unknown is totally n plus 1. Okay, good.
Okay, good. Thank you.
Thank you. Okay. Thank you very much. Okay.
And there is question or remark from Irina Denisova. She's saying in the case of equal viscosities, the jump of normal stresses is 0. So in this case, there is no interface.
In the case of equal viscosity, the jump of normal stress is 0. Why?
Let's think about it.
Yeah. Also,
No, but,
Sharka.
Yes.
Sharka, Irina have some question or opinion. Do you see the chat?
This is just opinion, yeah.
Yeah, the jump in the case of equal viscosity, we have the same conditions. We have the jump here is not 0. It's minus sigma k nu.
Yeah, because you have interface of these velocities and pressures. Yeah. So,
but also you can consider that the V plus minus is the same.
Yeah, but
this
does not mean that the left-hand side is not 0, because how is defined? Let's come back to the formula for stress. We have P plus and P minus, and we have V plus and V minus. So it's the jump of the pressure we have there in the jump, this jump, also the jump of the gradient of the velocity. The constants mu are equal, but
yeah, you have jump from velocities and pressures.
Yes, so
velocity is the
simpler
same,
because we can.
Velocity coincide on the interface.
No,
Yes,
velocity are coincide.
The velocity coincide by the gradient not.
Maybe.
This is different.
Yeah,
But
maybe.
So
okay.
the jump, the left-hand side is not 0. It's true, mu's are the same, but we have P minus below and P plus above, and we have gradient V below and above, and they are not equal.
Sure.
The jump is this one.
Yes. Okay.
That's okay.
Pressure on the normal component of velocity.
Yeah.
You have a jump. Okay. Good. Okay, very good.
Okay.
Okay. Therefore, one comment is also you quote the Professor Salonika and Jan Prus. Therefore, you should quote also my paper because.
Yeah, that's clear.
It's clear. Also the time evolution. But my papers appeared in fluid. It's not a paper. It's one chapter of a book. Of fluid fluid under something. It is Sharka is one of the editors. Right? Okay.
I will look for it.
2020.
Yoshihiro.
Okay.
2020.
Yes.
Okay,
Chapter 3 of fluid. Pressure under fluid. No.
Pressure under fluid.
Under pressure.
Yeah.
Sorry.
Yeah.
From 2020.
20. Yes. Professor Nichasova editors.
Yeah.
Maybe
here.
You can send me a copy, Yoshihiro.
No, it's a book. Therefore, I don't have the copy.
Okay, I will look for it.
Yeah, please.
Good. Thank you for your remark.
Yeah. So if there is no more questions or remarks, so let's thanks again speakers. So thank you very much for very nice talk and interesting. Yeah.
Thank you very much.